Ratul has been doing great work from the University of Washington on many topics. He's been getting many awards on his papers. And he went to Microsoft Research. Basically, from the university professor position he had, he went to Microsoft Research to continue his work on the topics of intent and connectivity and connecting all the network elements together. But now recently he has started a new gig, and I hope he's enjoying going from large innovation to now driving it from a small startup, as it's a pleasant journey. And stage to you.
Cool.
Thank you, Ratul.
Thank you, Per. So, oh wow, lights are bright here. Anyway, good morning, everybody. Like Per said, my name's Ratul Mahajan. Just a little bit of background. I think a lot of you may not have kind of seen me because I was kind of living the life of an academic, hiding inside Microsoft Research for the last 10 years, where with colleagues there, we helped kind of develop and kind of push to production a bunch of fundamental technologies that lie across those large-scale networks and whatnot. So actually, like, also want to thank Bruce for inviting me. I think, like, when he sent an email, his original email said, "Oh, do you want to come to FutureNet and give a 20-minute talk?" I said, "Sure, 20-minute talk. I can do that in my sleep." And I loved the event last year, so that was great. But then a week later, said, "Oh, do you want to come back and actually, do you want to give an hour-long talk?" I was like, "Oh shit, I don't know if I have things to say for an hour." So it took me 10 days before I finally said, "Okay, sure, I'll do it." Bruce is a good friend. I've known I couldn't say no to him anyway. But I'm actually thankful now, I think, because the length actually gave me a chance to synthesize what I hadn't done before of work that I've been doing with colleagues and customers at IntentionNet, but also my academic collaborators at Princeton, UCLA, Wisconsin, Madison, USC, CMU, and Microsoft. So what I'm presenting here is not just the work that I've done personally, it's collaborative work that's happening across the industry as well as academia and so forth in there. All right, so let me start off actually with like what might come across a bad joke. So I'm going to ask you a question, which is like, so a network engineer, a hardware engineer, and a software engineer walk into a bar. How do you tell which one of the three is a network engineer? Anybody? Okay, it's not really interactive venue, but you can shout out. Okay. Okay, so not a fair question. I made it up. The answer is the network engineer is the one that's sitting at the bar with crossed fingers and basically repeating every sentence 3 times in the hope that his message will actually get across in there. All right, so with that in mind, why are those fingers crossed? The fingers are crossed today because in network engineering today, there is a wide gap between intent and reality. So what do I mean by that? Like, I think as an engineer, when you try to build an artifact, you have this vision of this beautiful thing. In the context of networking, what you're trying to do is to build a highly available, highly secure, and a network that changes at the spin of a dime. Your new business needs come up, you want to be able to change it. So have this vision of this infrastructure you want to build. But what ends up happening tends to be far removed from what your intent is. And the reason for that is, for those of you who are not network engineers, let me just abstract away the process that happens or give you some insight into why their gap actually emerges. So you have this vision of policy intent. So you as an engineer or a group of engineers, you write down your policy intent into some kind of spec. This may be formal or not formal, depending on the organization. You translate that spec into the configuration of devices that will actually run on the boxes there. And these devices talk to each other, whatnot, and during that time, some dynamic state like ribs and fibs and things like that get populated. And when packets come in, the state gets looked up, and packets get traversed, and the actual runtime behavior of the network emerges. So the gap between intent and reality occurs because each of these processes along the way introduce their own bugs. They can be translation bugs from policy intent to the specification. They can be translation bugs from the spec to the device configuration. There can be bugs in device software or hardware that basically create bugs from the configs. You may have written the right config, but the dynamic state itself might be wrong. Or the dynamic state may be correct, but the runtime behavior might be in there. Today, basically, the most advanced capability we have today to debug these behaviors, so all these bugs are basically showing up one way or the other in the runtime behavior. So the hope tends to be that if I just monitor my network correctly, I will be able to catch all these bugs, and I will basically have an intent-based network. And I will tell you no. And the reason for that is network monitoring is basically both too little and too late. It's too late because by the time you find problems by monitoring a network, problems are already happening. So you have an outage, it has already happened. Host A cannot talk to host B, you find that using monitoring, it has already happened. If you find a packet that has breached an isolation boundary, that has already happened. So this is what I mean by monitoring being too late. But at the same time, it's too little because you get no correctness assurance whatsoever. Everything might be hunky-dory in your network right now. How do you know there's not a packet that will breach the isolation boundary tomorrow? How do you know if a new link were to fail, your network will not fail over, or backups are correctly implemented, and so forth? The monitoring will not answer that for you. A final problem with monitoring is that root cause analysis tends to be very difficult. And that's because monitoring is too low level to actually give you context. So for instance, if you see packets go across your network when they shouldn't, how do you know what's wrong? You only know bad things are happening. So root cause analysis essentially takes a lot of time. At the same time, some of you might be thinking, can automation help? Absolutely. Automation can help, but automation does not automation by itself does not guarantee correctness. So you should think of automation as you've just replaced your screwdriver with a power tool. It does not give you the guarantee that what you're building is correct in the first place, or will it stand the test of time and so forth and whatnot. So apart from monitoring, that's basically where we are. So when all of this stuff happens, so essentially what I would want to say is that what you really want to do is to catch bugs really early in the pipeline, because the later you catch them, the more costly they are. At the same time, damage has already happened and so forth. And the kinds of damages I think you guys are well aware of. When there's a gap gets created between intent and reality, you see outages, and you see, almost every week there's a major incident. You can read up on BGPMon or whichever your favorite outages mailing list is. Something or the other is kind of always failing, and there are lots and lots of outages that don't make the news, like the ones maybe you experience in your organization, so hopefully they're not making the news. The flip side of outages is security breaches. So outage is basically, two hosts that should be able to communicate, not being able to communicate is outage. Security is, when unauthorized or unauthenticated communication happens, that happens. A final thing that does not actually make the news outside of the networking circles is that in a lot of ways, like networks today have become the long pole in application delivery. Like it is the piece of the infrastructure that takes the most amount of time to evolve, to change to the business needs, and so forth. So in fact, with one large cloud company that we work with, we learned basically to make even simple changes like ACLs, it can take them a few weeks. That's because they're trying to be really, really careful as they evolve their network. So basically, this kind of gets in the way. So, and the end result of all this to the organization is very high operational cost and reputation damage to the company itself. So, the joke I was telling you about engineers, that was a false joke, because when that happens, nobody actually wants to go to the bar with network engineers in the first place in the company in there. So if I haven't scared you enough, I also want to point out that things, if we stay on this track, things actually will get worse. And they will get worse because of the trends that Pierre talked about a little bit. You have software and hardware disaggregation going on with white box switches and what that does is basically more moving parts, more tougher configuration, things become even harder to get right, and so forth. And you have more devices, not just end devices, you have more physical and virtual devices. And the number of devices that an individual engineer or a small team of engineers is responsible for also keeps increasing, so forth. So that's going to increase complexity as well. At the same time, transition to hybrid cloud. So now you no longer just have to worry about the physical structure you have. You also have to worry about how to extend this physical infrastructure that you have into the cloud and building a network fabric now that is much richer in terms of complexity and functionality and so forth. But we have not seen any kind of fundamental progress so far in our ability as a networking community to handle complexity. Yes, we have introduced automation, some bits of SD and whatnot. So yes, it's gotten slightly better, but it's gotten better not at the rate at which we would like it to be in there. So when we observe these trends, and I think the answer for what a lot of work that I've been doing with my collaborators is basically a simple one. The story we are seeing in networking today has been seen by hardware and software engineers before, like 20, 25 years ago. And that community essentially responded by building a class of technologies and processes to tame the complexity. So our idea here is a simple one. We should actually learn from hardware and software engineering communities and essentially bring to bear, in practice, similar approaches with a very, very strong foundation. And that's the only way we can actually increase our ability to handle complexity, tackle that complexity, and bridge that line upwards towards the inherently complex pieces of infrastructure we are building in there. So the rest of the talk, I'll talk about, add more color to what I mean here. In particular, I'm going to talk about 3 approaches that we should take from hardware and software engineering communities. One is formal validation. So build a network that provides strong guarantees on correctness so you don't have to rely just on monitoring to figure out when things are going wrong. So guarantee should be there in what you build from the get-go as much as possible. I mean, things will still fall through the cracks, but the idea here would be there will be much fewer cracks and much narrower cracks, just the way it happens today in hardware and software. There should be high-level intent specification. So we need to formalize those languages and what that means, whatnot. And a final thing that does not get a lot of attention is that to develop hardware and software, there's a lot of development tools available to engineers that are basically non-existent in the networking community. So it's not just about building fundamental technologies. They all go to waste if we actually do not manage to package those things correctly. That's where dev tools kind of come in. And my claim here is that if we do these 3 things as a community, we can provide strong correctness guarantees on the engineering artifacts that we are building. We can simplify intent expression. We can catch bugs really early in the networking pipeline, workflow pipeline that I talked about. And most of all, we can enable not just deploy new networks correctly, we can enable safe and rapid evolution of existing networks. So no network basically, you never just design, deploy once and forget about it. Networks fundamentally are about evolution. So how do we actually do that? I think if you do all of that, you get these 4 things in there. All right. The other thing I want to say is that this is not just a pipe dream. I think the networking research community has responded over the last 5-6 years to these problems of inherent complexity. I'll talk a little bit about it, but at the same time, I think other speakers in the next session will also talk about similar things, how they've taken some of the research ideas, or they're taking some of the research ideas to production. So the point I want to make around that is that all of this stuff is doable today. And it's doable today because as a research community, what we've built is very precise models of the networking control plane. So we can take the entire network operation, understand it mathematically, and reason about it mathematically in there. And all of these things like formal validation, high-level intent specification, and development tools can be built today based on the foundations that have already been laid. OK, so let me get started. So I'm going to talk about formal validation first. To give you some clue, or like in terms of how far behind, take that back. Let me first define formal validation. So formal validation basically means, for the purposes of this talk, it's comprehensive analysis of certain aspects of network behavior. So what I mean by comprehensive analysis is that I want to validate correctness of the network behavior for all possible nodes, endpoints in the network, for all possible packets, or maybe all possible failures, and maybe even all possible routing announcements that the network may get from the outside. Because each of these things are different. And what I want you to think about is like how different this is from testing. What testing will do, if you log into a box and do a trace route, that is basically testing. What it's doing is that it's checking whether the network's behavior is correct with respect to the trace route packet you just sent. That is, nothing more. It does not tell you that a different trace route done from a different source will have the same experience. It does not tell you that if you change the header of the packet you sent, you will not have a different experience. It will not tell you that if a failure were to happen in the network, the trace route will still work. It will not tell you if a routing announcement were to come in from outside, it will not screw with your network. So what we're trying to do here is to give comprehensive guarantees. To add a little more color, what that means is, suppose you want to give these guarantees. That should basically the domain of formal validation. Is the DNS server globally reachable? Not just from one place where you did a ping or a trace route from everywhere. This is meant to be a globally reachable service. 2 subnets that you wanted to isolate, are they really, really isolated with respect to all traffic, not just that one packet that you happen to send to test for isolation? If you have a data center and you're trying to deploy spine routers, can you guarantee that these 2 spine routers treat all destinations identically, such that if one of them were to fail over, no connectivity change ever happens? In reachability, can any encrypted packet go from A to B? Will any interface failure lead to any loss in connectivity whatsoever? Can any external announcement disrupt internal connectivity? So what I want to focus on, the highlighted words, is guarantees being comprehensive with respect to all nodes, packets, failures, and routing announcements. Finally, is all communication with the device properly authenticated. So with these examples, I just want to get across the idea what it means to actually do formal comprehensive validation in there. So getting the point back about like how far behind networking community is, like if you look at hardware engineering tool chains, so go to Mentor Graphics, Cadence, Synopsys, all these kind of storage companies for EDA, electronic design and automation, you can find and use a suite of tools to give you formal guarantees on a lot of aspects of the hardware you're building. And for network engineers, what we have today is basically ping or traceroute. That is it. That's the state of art when it comes to validation. And they are great tools to use, but like I said, hopefully you understand now that they are not enough because in there. But thankfully, this is one domain where networking research has made a lot of progress in the 5-6 years. In particular, take this pipeline. And I'm going to break out those validation technologies that exist today in 2 big buckets in there. One is what gets known as data plane validation. So data plane validation, what it does, it starts with a concrete dynamic state. So these are your ribs and fibs and other things, SNMP, MIBs or whatnot, get populated. And it analyzes the current network state with respect to all packets that the state may encounter. So you've taken your fib snapshot, and you're going to answer much better than ping or traceroute because you're giving answers for all possible traffic. So you can say, OK, given this dynamic state in the network, no packet can go across the isolation boundary, or DNS servers globally reachable and whatnot in there. And there's been a series of kind of more sophisticated tools, from header space analysis to Veriflow to DeltaNet. You can go read the papers if you're interested what this works. The thing about data plane validation, as great as it is, it's not enough. It's not enough by itself because when failures happen, when new routing announcements come in, a different dynamic state gets generated. So data plane validation is telling you, is my network correct right now in the moment or not? So to deal with that limitation, researchers went down this path of what gets known as control plane validation. So what control plane validation does is essentially reasons about the control plane of the network itself. So you are reasoning about configs and all possible network states. So think about logically. Don't worry about how it gets done. But by reasoning at the config layer, you have a model of the control plane, and you're reasoning about all possible dynamic states that emerge. So for those of you who have a software background, to give you an analogy, control plane validation is more like reasoning about the program itself, what gets known as static analysis. And data plane validation is more like dynamic analysis. The program runs. It generates new heap structures, new stack structures. And you can take a snapshot of the heap and reason about it. There are no memory leaks. Or you can go front in the pipeline and reason about the program itself. That's the basic difference. So in the networking context, this is what it basically means. So these are the same 7 questions. What data plane validation can do, it can answer some questions for only the current network state. So it can answer these 4 questions: DNS server globally reachable, subnodes isolated with respect to all traffic, spine routers, treat destination identically, can any encrypted packet go? In contrast, what control plane validation does is it can answer all of these questions, in theory, for all possible network states. So not only those 4 questions, like take DNS server globally reachable. So the difference in the guarantee would be, if it tells you a reachability guarantee, it will hold for all possible failures and routing advertisements as well, not just the current state, which will change when those things happen. There. In addition, control plane validation can answer these 3 questions, like any interface failure lead to connectivity loss, any external announcement disrupt internal connectivity, is all communication with the device properly authenticated. And the last one is because there are things in the control plane that don't filter down into the dynamic state at all, control plane validation to do that. But just to be clear, I don't want to leave you with the impression that control plane is basically a perfect superset. It's not, because it is building a model of the configuration. And in cases where device software bugs happen, data plane validation may still be useful in there. Because inherent in control plane validator's ability to generate all possible states from the config itself lies essentially models of how the device software is meant to behave. And that's an assumption data plane validators don't make in there. But I just want to give you a flavor, logically, how to kind of think about these things. OK, so getting a little bit into the how part. So I'm going to explain things in the context of control plane validation, because that's kind of the stuff that my research has focused on, and my company also focuses on. But you can read up on that. I think the academic research is open. You can go to batfish.org, and their point is to papers. I've listed there a couple of papers. You can take a look in the nuts and bolts, how are things working. If you like to read academic papers, that's your source. Or if you want to play with code, there's code as well there. So what control plane validation does is we'll take in as input your configurations, any other metadata or dynamic state of the network as an optional input. It'll take in your intent, and I'll talk about intent specification in the second part of the talk. And then it'll tell you, hey, these set of intents are met, these set of intents are not met, and so forth. And the way it works is that internally, it will build essentially parsers and ASTs, so abstract syntax trees. From these parsers and ASTs, it builds network models. And then it uses analysis engine based on the model itself. So these analysis engines are things like very similar to those used in the hardware domain, like SMT solvers or SAT solvers, theorem provers, constraint solvers, and so forth. It'll use something that's appropriate to the model being used about. What's really kind of new here in terms of, so those analysis engine, most of them, what we've done is they've taken off-the-shelf solvers. What's kind of new here is how to actually model the network more formally. So in particular, you build multiple types of model depending on what you want to check. An example model you might build is simply a vendor-neutral data model of the config itself. So in this case, this YAML style thing. So this will not depend on whether you have a virtual router, a Cisco, or Arista, or Juniper, whatnot. So when you can write checks on it, it builds models of the dynamic state itself. And a third category of model that's kind of very interesting is that it takes the whole network and turns it into a set of equations. This is where true verification actually kind of comes in. And it's a very powerful model. So what it does, and this is once you build these models, you can ask for any constraint whether they are violated or not. So in the next few slides, I'm going to just give you a flavor on how to take a whole network and turn it into a set of equations. Those of you who don't like math and algorithms can just sleep off for the next 2 minutes. But I didn't think I could give a talk without a little bit of math and algorithmic stuff in there. So, but just 2 minutes, so stay with me, I promise. So, but my idea is you're not going to get the algorithm but hopefully you'll get enough intuition as to what's going on. Take this network. Let's say our goal is to turn this into a set of equations. R1, R2, R3 are the 3 routers we control. N1 through N3 are our external neighbors. S1 through S3 are 3 subnets. The first thing we do is to have a more protocol level breakdown of the network. So R1, R2, R3 are running BGP outside. They're connected to 3 subnets, and they're running OSPF internally. So you can see the 3 logical processes going on. Take this view, then focus in on what happens at the BGP process of R1. Essentially, what's happening is information is going in and out based on which this BGP process's behavior changes. You can redistribute connected routes to BGP. That's what's happening. BGP messages are going back and forth. So this is what's happening, right? So as a first step to turning the network into a set of equations, you basically say, OK, these messages are symbolic. So what I mean by that is these things like valid, prefix length, they are essentially variables. These are not concrete entities in the network model. So we take that. So that's kind of first step. Messages are made of variables. Then you can turn all your filters that you have into a set of logical constraints like that. So for instance, I think it's hard to translate in real time. Essentially, if you take the first line of the import filter, prefix list deny 192, 168, 1613, you will see that how it actually maps to the second line there. You can see what's happening. FBM match for first bits match and whatnot. You're essentially taking the filter, turning the logic, and then we take the entire network and the symbols and basically tell you, is there a failure under which some constraint will be violated? Is there a routing message under which some constraint will be violated and whatnot? At this point, you might be thinking, my network is too big. There's no way that I can translate all of these equations and still get answers in real time. And I can tell you, we've done these experiments. And control plane validation like that does scale to large networks. So this is just kind of one experiment. Maybe you want to focus on the bars on the right with 400 routers set up in a data center topology. You give you a sense of the properties we are checking. So no black holes. And I want to remind you that this is like control plane validation. So when this validation gives you guarantee that no black holes, it's actually telling you under no single interface failure, under no routing announcement from outside, there will ever be a black hole in your network. It's not giving you guarantees just on the current flow. It's checking multipath consistency, which basically means if multipath routing is on, packet should be treated similarly across all the paths, and the length should be the same. It's telling you local consistency. Are 2 routers in the same row, let's say spine or ag layer, are they same? It's telling you whether TORs are reachable or all TORs are reachable, whatnot. And I can explain these properties and go on and on. But the point is that even on large networks, this whole finishes in kind of under 5 minutes in there. So the nice thing is this is not like an online thing. You design your configs, and you get these strong guarantees in a few minutes. and you deploy with your peace of mind, essentially. That's the value proposition here and there. I also don't want to give you the impression that all problems are solved in network validation. They are not. So I would just want to list out a couple things. For instance, I think we currently do not know how to actually scalably handle special types of packet handling. So if you have like a deep packet inspection-based middle box, or if you have stateful packet transformations, we don't know how to handle them at scale right now. But I'm confident things will emerge over the next few years where we will be able to do that. Things like NATs, which are kind of static, can be dealt with. But it's kind of more tricky middle boxes that are hard to capture. Performance, we don't have a good handle on how to reason about performance. So for instance, if you wanted guarantee that is there a traffic matrix that will lead to buffer overruns, we can do it. We just don't know how to do it scalably yet in there. OK. So let's move on to the second piece of the talk, high-level intent specification in there. I was told I could take like questions in the middle. So if anybody has a burning question, you can ask now. Otherwise, I'll just shut up for a second and give you a breather. Sure.
Are you validating only the configurations as you create, or are you creating a metadata repository that is constantly observing the configuration across the network?
So the answer is both. I think the way to think about what I described was a core technology. And we can discuss essentially how you package it. You can package it in both ways, and that's some of what we're doing. You can actually package it in a way that is basically becomes like a deployment gate, or you can package it in a way such that it's doing like constant, kind of like a guardian angel, constant monitoring. So it really depends on like what the engineering workflow at a particular organization looks like. And I think there are different ways to just package the same equation solver, so to speak, there. Make sense? OK, so let's move to high-level intent specification, so I can tell you what's kind of happening there. The goal here is simple. We want to let network engineers formally express intent at a high level, and once they've done that, basically automatically synthesize device configuration from that intent in there. If we do this right, what we would have done, we would have reduced the gap between intent and specification, which is a big gap today, and we would have guaranteed correctness for synthesized configurations, just like assuming our compiler is correct. But compiler bugs are rarer than networking bugs induced by network engineers' mistakes. So take it for what it is. That's basically the two key advantages for high-level intent specification. The way kind of I think about intent specification is that there are two key axes here. One is that are you designing an intent specification method for any kind of network, a general network, or are you focusing on specific designs of the network? A second axis is that are you specifying intent at a device level, or are you specifying intent more globally at a network-wide level? So to give you kind of flavors, so things like Cisco iOS and even OpenConfig sit at top left. Because you can use these kind of technologies, so to speak, to program any network, not just specific designs. But you have to specify what individual devices should do, not what the network-wide behavior should be like. At the other extreme, you might imagine there are things like Cisco ACI, and my limited understanding of Apstra might also kind of sit there, but I will not put money behind that claim. The idea here is that what these technologies have done is that you specify what the network should do as a whole, but what you've lost is generality. They focus on specific designs like a data center fabric with the closed topology and whatnot. But the thing is, like, we are building a lot of networks. So an interesting question for us when we kind of went down that path and thinking about it about 5-6 years ago, does this world exist where we can have a network-wide intent specification language, not a shrink wrap system, that works for general networks? So why we wanted generality should be clear. But I'll give you some insight into those who don't do kind of distributed routing configuration programming, why we actually want network-wide specification. So take this example. The network you are responsible for is the yellow one in the middle. And you basically have very, very simple intent for this network, that there should be no transit between x and y. You should prefer C over B over XY. And you should prefer Z, use Z only for that particular prefix over there. To get this policy intent right today, if you were to specify that at device level, first of all, you will have to tag, as an example implementation, you will have to tag all announcements coming from Y, tag them so that you can block them at X. If routing announcements can flow from Y to X, data cannot flow from X to Y. For those of you who don't know BGP. Similarly, you'll tag it in the other direction. So that's kind of the first policy. Then you'll add some local preferences to do kind of C preferred over B. Then you do some filters. And so you're basically doing this really low-level assembly-like things. And imagine doing that for a network of tens or hundreds of routers, whether you have tens or hundreds of neighbors. This is where a lot of stuff breaks. So how many people know how to configure BGP in this room? OK, so there's a bug here. Who can spot it? See, it's not easy. That's the point. OK, good. So the bug here is that the local preference on B should have been higher than local preference on A and D, because the preference goes from C and B and then XY. So that order has been inverted, basically. So one number you get wrong, and you have incorrect policy, and you are programming essentially hundreds of these numbers, basically. And this is hard. It's like but flying just over the weekend, just a weekly browse, and just an example of the kinds of things that go wrong with BGP. This is like major leakages of routes that caused outages in Japan and beyond because of some interaction at Google and Verizon's route filters and whatnot. So even the most experienced of players, or what you might think of as the most advanced players, are making mistakes today. Because this stuff is not that they're doing something wrong. I think this stuff is complex, and we do need fundamentally better and different tools to actually make this stuff work in there. So that's why I think when we went down this path, OK, we want to experiment with something that can express general networks, is network-wide, because this device-level specification business is actually very difficult. So the world we want to aim for is, this is today, the world we want to aim for is that the engineers expresses policy in what we're calling the propane language. From propane, we have a compiler that automatically generates BGP configurations in there. Again, I think you can go to propanelang.org and read those papers that give you more insight into kind of what's going on. And the code and the compiler is all kind of open source as well. And you can build essentially any network today if you wanted to use there. So what does propane as a language look like? So this is like network-wide specification. So essentially, if you want the no transit rule, in propane, you'll simply say no transit true goes to no transit. True basically means the policy applies for all prefixes, not just a specific prefix. If you want to specify preference, again, you say, OK, I prefer to, for any prefix, they're again true, I prefer to exit through C, then through B, then through XY, and so forth. And we call this ownership. These are sub-policies you're defining. And you basically say all valid paths in my network for that particular prefix, 16.4.0.0.16, should end in Z. So just see how direct the translation is from the English policy to this propane language. That's what we're going for. And finally, you say my policy is the combination of these three sub-policies. And the compiler will combine them in some meaningful way. And it will generate all these kind of low-level mumbo-jumbo that I was earlier talking about. And just in case you're paying attention, it actually generated the right local preference here. That's by design. It's like, OK. So that looks like the propane, the language. What does propane, the compiler, look like? Propane, the compiler, is essentially, I think it's taking two very different levels of abstraction, a network-wide specification of data flow, to a device-level specification where you're tweaking BGP knobs and local preferences and filters. And like any compiler that is bridging this abstraction gap, you go through kind of multiple sequences of intermediate representations, which in propane case tends to be a three-step process. Go to regular IR, do a reverse automata, and I will explain these things in a second, and do a product graph. So in these three, I'll explain these three steps in a second. But I do want to warn you now. OK, I think we're slipping back for another 2 minutes into the math section of the talk. OK. So, and I forgot to wake up the rest of you who told you to sleep off in the last section. OK, again, my goal is to not actually tell you how the exact algorithms work, but hopefully you get the flavor what's happening. OK, so take an example like this. You are controlling this, again, this yellow circle in the middle has two neighbors, X and Y. And your policy is that you prefer, for a prefix P, path X ACDY over any other path in the network. So you want to go from the top, essentially, is your preference for whatever reason. And you want paths to end in Y. So you can compose policies like that. Now the question is, how does Propane take this policy and that network and turn it into its BGP configuration? 3-step process. Compose these wishes into what we call the regular IR, which is describing essentially nodes in the topology. So we've basically taken that and composed over things. So one of the things the compiler does is extends the semantics of regular expressions to have preferences. So x, a, c, d, y is prefer over anything else that ends at y, basically. Take that, turn this into essentially what we call reverse automata. Its reverse is because it's tracking the flow of BGP messages, which flow in the direction opposite. So so basically what this saying is, to get the data path x, a, c, d, y, your BGP message should go like y, d, c, a, x. And similarly is happening. So step 2. Step 3 is the most interesting one, where we take the topology and the reverse automata, and you can almost think of this as taking the Cartesian product of the topology and the policy, and you get a thing like that. And those numbers at the bottom, it tells you the preference of the path. So if you focus on the path on the extreme right, you will see essentially y, d, c, a, x that has a preference. That's your first preference. I'm going to end there. Essentially what hopefully you get the idea that once you have this, we translate into BGP filters, essentially. So because each of the edge becomes a routing filter, and communities can encode, so we have a way to encode that, and we get the BGP policy in there. And that's because this product graph has the property that is capturing all possible policy-compliant paths, no more, no less, all policy-compliant paths for BGP messages. So this is the tool chain in there. What you get for doing that, the guarantees, is that the generated BGP configurations will be policy compliant for all possible failures in your network. There is no failure for which your path preferences will not be respected. There's no failure for which the traffic will ever take a non-compliant path, so forth. This is a very strong guarantee. The other very strong guarantee you get is with respect to, I was talking about no network ever kind of deploy and forget about it. You need to evolve. The other strong guarantee you get is that only neighbor configurations will change upon link addition or removal. So you can grow your network or shrink your network, and the number of devices on which you'll have to change the configuration will be minimal, essentially. That's the guarantee you're getting in there. And that comes from some parts of Propane I didn't describe around encoding your topology as well in there. OK. So a big test for high-level specification languages tends to be, is it expressive enough for my job? So what we did here was take essentially a data center network and a backbone network of a large cloud provider and say, OK, they had their policies in English language. So OK, can we convert that English into something formal like Propane? So what we found was that once you take away all the constant and macro definitions around where the prefixes are hosted, you basically could express data center configurations in only 31 lines of Propane. And that's coming from, essentially the language being very high level. So think about, your data center is basically saying all paths should go up and go down. So that's kind of like, that's why it's so compact. And similarly, we took all backbone network policy written in English again. And that was basically 43 lines of code that the engineers were writing. And from here, essentially, Propane generated BGP configurations that were about 10,000 lines. And those configurations were actually on par with what the engineers were writing today, around 10,000 lines of BGP configurations and whatnot in there. So it gives you a level of kind of complexity difference, like how easy it is to program in a high-level language, let's say Java, C# versus assembly. That's kind of like in terms of blow up lines of code. That's one way to intuit what's going on there. OK, so Propane is essentially kind of one take at high-level intent specification. Again, I don't want to leave you with the impression that all problems are solved. I think there are problems that we don't have answers for here in there. Two particular ones is like you might think like it's unclear what the right altitude is for intent specification. Earlier I was talking about general purpose versus specific designs and whatnot. Propane is kind of somewhere in the middle that is not device level, it's network wide, but it lets you do general things. I think we as a community don't quite know yet, or I would posit that. What is the right altitude at which intent should be specified? Maybe the answer is different for different networks for all we know. And this is kind of tugging into, does there exist one language for all possible concerns around routing, security, performance, or we need more specialized languages? The software engineering world definitely has specialized languages for different things. You have all kinds of domain-specific languages and whatnot. Maybe that's what networking needs. So I don't know what the answers are. But what I will tell you in general, given a kind of hard engineering problem like that, The people who succeed are the ones who can experiment the fastest. The Wright brothers essentially won the race to have human flight, not necessarily because they were smarter. They won because they could iterate really, really fast on their design. So they could design something, try it out, doesn't work, improve, design it, iteration. So I think to hit upon the right intent specification languages and frameworks for networking as posit, we basically need to be able to iterate very fast. We shouldn't be inventing ITF drafts for 5 years that then go to dumpster. Rather, have a more nimble approach where we can try different things, see what works, what not. The danger with trying different things is like, what if you fail? I'm here to tell you that you will not fail. And the reason you will not fail is that the control plane validation technology that I was telling you about earlier is basically a safety net. You can try different systems for intent specification and config generation, but if validation is in place, your network will not break. So you could have homegrown intent specification mechanisms you want to play with, but have control plane validation as a safety net, and there's a guarantee that you will not break your network. The guarantee comes from the validation technology, not the intent specification technology, so that lets you play with different intent specification technologies on the front end. It's not just that. You can also safely make tactical changes. I think this does not get a lot of attention, but when I talk to our customers or real engineers, like nothing's perfect. You have to go into a box. There's no other fix for that software bug or some design change where you have to go in the box and actually make changes to the BGP or OSPF configuration manually. There's no getting around that. And these high-level systems have not caught up yet. So I think if you have control plane validation change, you could generate most of your configuration at a high level and then go making changes and yet be given the guarantee that the resulting system is safe. Taking that one step further, you could actually have different languages for security performance routing. They can all individual correct compilers, they can come together, and you can then reason about the correctness of the ensemble in there. Because today, if you were to do that, you will get no guarantees. Even if these individual compilers were correct, who's there to tell you that the whole ensemble is correct? But with control plane models, you can essentially do that as well. All right. Again, I'm going to give you a breather. Any questions? Dave?
So one of the challenges of building a BGP design or work in a large-scale network is actually things about performance.
Mm-hmm.
Some of the rewards and twists that you get in a BGP architecture is dealing with the fact that convergence times, either because of the number of routes that have to be propagated,
Yeah.
or just the CPUs of the processors. How do you take things like that into propane if you're automating generation? Fix it, you can build it?
So there's some guarantees you'll get just by design. And there's some guarantees we'll talk about in terms of language enhancement, and that's a great conversation to have. The short answer is we don't have all the answers today. A slightly longer answer is that some of those things can be automatically reasoned about. So things about like max prefix length, right? You can specify, just like for compilers, you specify hardware constraints. You can give those constraints to the compiler itself as part of your topology, that this is the max rib size I want, this is the max filter. The nice thing now would be that compiler will generate something that's correct by design. So your prefix max prefix constraint will not be violated kind of by design versus because you can reason about filters and things like that. So I think the world will kind of end up in a better place, I think. But certainly, I think if you will have to think about like how to actually encode all this information. I think max prefix length is a simple one, but some of these other ones I think we're kind of thinking through. But I'd love to kind of hear more. Yeah. Yes, sir. At the back. Sorry, I'm having trouble hearing you. Do you want to just come up to the mic, please?
So basically, you have three elements, right? Wi-Fi, LAN, and WAN with respect to a network.
Mm-hmm.
I'm talking about high level.
Yeah.
So the presentation you make is more specific to WAN point of view, or can be enhanced to all three network elements?
I think there's no reason it can't be. And I think it's just simpler. As a context, it's easier to understand. It's not just WAN. I think we certainly work with data centers and kind of campus networks that include Wi-Fi routers as well.
And the work which you guys are focusing on the WAN part as of now?
I think the work itself is kind of more general than just the WAN. I think that's part of focus in the sense of, I think, your ability to understand the configuration of a box does not kind of vary as much where that box kind of gets deployed or what environment. Those models, underlying models are general. They are models on what configuration does, what happens to a packet and whatnot. And we are applying them to all sorts of environments.
So let's say I manage a production network. So if I have to look at some real-time deployment scenarios, as of now, the ability to do that is in the WAN segment. But let's say it has to be evolved into LAN and the Wi-Fi. It's something which you will look into the future point of view, right?
I think Wi-Fi as a practical problem we haven't tackled, but LAN and data centers and WANs are perfectly, it's things we've done.
Okay.
And yeah.
Okay, thank you.
Right. Yeah. Yes, sir, over there.
I see how you apply physical networks, but once you have a virtual network with virtual routers, virtual switches, virtual zero boxes, the network's changing in seconds, maybe minutes. What are your thoughts on how to apply this technology to that network?
Excellent question. Let me say, like, I'm going to throw out some packaging ideas that address that question, but ask me again if I haven't answered. Yeah. Okay, great segue. Cool. So then the last part of my talk, I'm going to focus on dev tools. And I'm going to define these are very simple. Like, what we want to do is to essentially package whatever I've told you into tools that are embedded into the network engineering workflow. So this is not a separate call. So think about like how software engineers work today or hardware engineer works today. They don't need to specify, what they need to run. Things automatically get set up in the workflow, and basically, they get run. Just for instance, I think like, our head of engineering, Dan, he just downloaded like a plugin for IntelliJ, and all of a sudden he found like, tens of code bugs that were sitting there for the last 2 years, whatnot. So things like that exist today in the software land. I don't know why they don't exist in the networking land. And I think the third part is like, we should actually make that happen. So all this validation and synthesis I'm talking about, and all these great questions that I think you guys are asking is around, in my view, is like, how do you take these technologies and package them as part of a development tool framework, whatnot. So if we do that right, by the way, I think we can make these things applicable in various different ways. We can also accelerate the design and change process. Think about writing software without good compilers, without good validators. It will be a very, very slow process, even if you get it right. So the value of that workflow embedded tools comes from doing it correctly and doing it rapidly and doing it with some kind of peace of mind in there. To give you a contrast about what we're talking about, if you go to the software engineering timeframe, you've got unit testing, continuous integration, linters, jet code detection, type checkers, style enforcers, debuggers ID, and the list goes on and on. If you're building a complex software engineering artifact, you have all of that. What do you have in networking today? You have VI, basically, text editor. And if you can figure out how to get out of VI, you have Emacs, And sometimes it's even harder to get out of Emacs as well, right? So that's the extent to which the state, and I'm not exaggerating, I tell our candidates, I'm not exaggerating here. You can, that this is basically the dev tools that are available to network engineers today. And that's something we have to change. So the promise here again is that, so it's all not doom and gloom. The promise here is that the control plane models I was talking about, and along with the parsers, abstract syntax trees, and the models of network behavior, as well as like, the high-level languages and whatnot, they have already given us a foundation to build a rich array of dev tools. So I'll run through a kind of mix of these to give you some intuition. So if you want a linting and dead code detection, feed your configuration into a box, like a plugin embedded into, maybe Emacs. And because you have those models, now you can automatically say, hey, you have 3 undefined references in your configuration. You have 25 unused declarations. You have 1 device with the non-standard NTP. Line 3 of ACL peer is unreachable. Based on those models, you can quickly do that linting, dead code detection, and so forth, and essentially iterate a lot faster. You don't have to wait for code reviews by your peer engineers to tell you, hey, you got some bits wrong in there. You wanted unit testing, okay? So feed in your configuration, and you feed in your unit test. Like, so all devices must be password protected. All interface MTUs must be greater than 1,500, and so forth. Again, the models we've built, let's say vendor-neutral data model that I talked about, can be dealt, and you can say which unit tests pass, which don't pass, and if they don't pass, you don't commit, essentially, just like with software. You want continuous integration, and this, I think, gets to the gentleman's point there. You define your configuration before you push it out. Just like today, no software gets pushed out without a battery of tests that go through a continuous integration unit testing toolchain. And yet, we are pushing out new network functionality without appropriate checks and gates. The right way to do this thing is known. We just need to do it, right? So if it can be made to work for networking if you're pushing configuration. So don't just push it. You take your planned configuration, have your unit test and continuous integration test defined, and throw it at a validation model and say, OK, if it passes, deploy it. If it doesn't pass it, fix it before you deploy it. So you have to really kind of get into the deployment tool chain to get some of these benefits of that nothing bad ever pushed out. And because it will be automatic, it can take care of changes that are being made every second, every minute, with guarantees that things are actually not going to go wrong at all. The final one is change analysis. I think this is something we can actually do better than the software guys are doing, because we understand the semantics of networking, or what the networks are supposed to do, which are a little bit simpler than arbitrary code. So we can do very rich change analysis based on these models. You say, this is my known working configuration, this is my planned configuration, and these models can tell you today that, hey, flow A is blocked in the planned configuration, while it was not blocked in the reference. Flow B takes a different path through the network, and this would be guarantee for all possible flows in the network, by the way, in there. So you can look at these changes and say, OK, was this my intent or not? If not, rinse, repeat, fix it. There's in there. And there. All right. So to summarize, essentially, I think what I'm arguing for, essentially, is a different type of a network engineering workflow. So this was the workflow kind of we outlined. And this is where the world is today. You basically go through these 3-4 processes, and as the last process, you essentially do monitoring, and monitoring is great. I think I'm not going to argue, don't do it, actually do it. But monitoring, as I've argued, is not enough. It's like too little, too late, finds problems after the fact, gives no guarantees on correctness, and root cause debugging is hard, which is why I think we should couple monitoring with formal validation of both the device configuration and dynamic states. This is possible today using the network models that we built. Should specify intent at a high-level framework. At the same time, engineers should be using dev tools that are easy to use, embedded in a networking IDE that understands the languages, understands the semantics, just like the way a good Java IDE will understand the Java semantics in there. And if we do all this right, we can provide strong guarantees on correctness of the network, just like hardware engineers and a lot of software engineers have strong guarantees on the correctness of the engineering artifacts they are building. You can simplify intent expression, reducing the gap between intent and reality. This is the longest pole today when things go wrong. Catch bugs early in the pipeline. As I told earlier, catching these bugs earlier is much cheaper, is much faster, leads to a lot less heartburn. So we should be trying to catch in this workflow, what is the fastest I can catch a bug, essentially, is the way you should be asking this question. And finally, we can enable safe and rapid evolution of the network as well. And hopefully, I think the reason I was going into technical guts was not to torture you, but I wanted to convince you that the network models exist, and all of this is actually kind of possible today. As a community, I think we just need to get our act together. I think the building blocks are there, and we can actually put them together today. And with that, I'll end. Thank you. Right. I don't know if you have time left, but I'm happy to take questions if there's time. So, yeah.
So what's possible? Is this an example where the real network is providing this?
Mm-hmm.
Second, where is the boundary where the config is coming out of this process gets mapped within a specific CLI or
So the question was a two-part question for those of you who didn't hear. The first one, if I understood correctly, that is it actually possible today? Is it happening? And the second was, where's the line between vendor-specific CLI and maybe a high-level intent specification language? Yeah. So the first part, yeah, it's possible today. I think we are definitely running things in real networks. I think how it gets packaged, there's no standard. I think so what varies in our experience is not the core technology. I think what we are experimenting as a company is that every network seems to have a very different workflow. So I think we're learning essentially how to kind of package it, and we kind of package it up. But the thing is, like, the technology is ready, it kind of gets used. In some cases, before things get deployed. In some cases, right after they get deployed, if they are kind of pulling configuration and whatnot. But the rest of the hardness is actually the core center is basically the same that gets used. It's just a matter of where, the other way to look at it is like how the inputs come to the analysis service change. Sometimes they come before deployment, sometimes they come right after deployment. And where the output goes changes. And again, and that depends on the exact workflow you have in your network, because there's no one workflow that any organization, every organization follows, because there's no standard in networking today that, you have a make file, or you have like Jenkins or something like that. So that's where some of the thinking kind of goes in. The line quotient is actually, so the second quotient is like the line between intent specification and formal validation. I think there's basically in our experience no line in the following sense, that these formal validation tools, they are working off of, because they have parsers, they are working off of CLI commands themselves. So you can feed in essentially what's running on your box. And there's some engineering required. So take those parsers, turn it into something a little bit more abstract. But you could take a high-level intent specification language itself and turn it into that model. And the way this works is like in the same way as like LLVM, I don't know if you know in the software engineering land, that kind of works slow. So you have your source language that people see, but underneath the covers you have this kind of lower level, more general language that you can map multiple source languages to. And that's where I think kind of from just a software engineering standpoint, that's what I think kind of Batfish does and Propane does, and that's just kind of the right way to do things. So in that sense, you have essentially parsers for different languages. They all map back to a common model of text, the vendor neutral data model I was talking about, and from there, all the analysis kind of happens in there. So you can this is where a lot of power to mix and match and do composition analysis also kind of comes in. Yeah.
Just want to get the expert opinion. Isn't artificial intelligence?
The best definition of AI I heard was appearance of intelligence. If this appears intelligent to you, yes, it is AI. If it does not appear intelligent to you, it is not AI. So you take your pick. Yeah.
I just want to get ahead of the marketing. We're in the marketing holiday.
I'm an academic, right? I don't know. Yeah, we'll figure that out. Maybe you can tell me in an offline conversation what the best way to market is, and I mean, from our perspective, we'd like this stuff to get used, and whatever makes people comfortable with using it, we are willing to kind of, yeah, but yeah, right. Well. If nobody has any more questions online, come grab me offline, and I'm happy to chat. Thank you. Yeah.